Hello everyone. Today we'll discuss volume of distribution, or VD, a fundamental pharmacokinetic parameter. When a drug is administered, it doesn't stay confined to the bloodstream. It distributes throughout various body compartments: plasma, interstitial fluid, intracellular fluid, fat, and tissues. The extent of this distribution is described by the theoretical parameter, volume of distribution. VD is the apparent volume a drug would need to be uniformly distributed in to produce the observed plasma concentration. Mathematically, VD equals the amount of drug in the body divided by the plasma drug concentration. For example, 500 milligrams of a drug with a plasma concentration of 10 milligrams per liter gives a VD of 50 liters. This means the drug appears distributed in 50 liters, even though total body water is only about 42 liters. VD is not a real volume, but a hypothetical one indicating the extent of drug distribution. The body can be considered a series of compartments for drug distribution. The plasma compartment, about 4 to 5 liters, is for drugs highly bound to plasma proteins, like warfarin. Extracellular fluid, about 14 liters, is for water-soluble drugs, like gentamicin. Total body water, about 42 liters, is for small, lipid-soluble drugs, like ethanol. Tissue binding sites and fat stores are for lipid-soluble drugs like diazepam, chloroquine, or amiodarone, leading to very large VD values. Several factors affect VD, including lipid solubility, protein binding, tissue binding, body composition, and pH. More lipid-soluble drugs cross membranes easily and distribute widely, increasing VD. High plasma protein binding restricts distribution, leading to a smaller VD. Drugs that bind extensively to tissues have a larger VD. Body composition changes due to obesity, edema, dehydration, and age alter body water and fat, affecting VD. Ionized drugs stay in plasma and interstitial fluids, while unionized drugs penetrate tissues more effectively. The most practical use of VD is in calculating the loading dose to achieve a target plasma concentration rapidly. Loading dose equals VD multiplied by the target plasma concentration. For instance, if digoxin's VD is 7 liters per kilogram and the target concentration is 1 nanogram per milliliter, the loading dose is adjusted for its large tissue distribution. Drug half-life depends on both VD and clearance. The half-life formula is 0.693 times VD divided by CL. Thus, drugs with a large VD tend to have a longer half-life. Drugs with large VD can act as reservoirs in tissues, like chloroquine accumulating in the liver and retina, explaining its prolonged action and potential toxicity. Here's a table summarizing drug classification based on VD values. Drugs confined to plasma, like heparin, have a VD of 4 to 5 liters. Drugs in extracellular fluid, such as aminoglycosides, show a VD of 10 to 20 liters. Drugs distributed in total body water, like ethanol, have a VD of around 40 liters. Drugs extensively distributed into tissues, such as chloroquine or amiodarone, have a VD greater than 40 liters, indicating deep tissue stores. A low VD, less than 10 liters, means the drug is largely confined to plasma. A moderate VD, 10 to 40 liters, indicates the drug distributes in extracellular or total body water. A high VD, greater than 40 liters, means the drug accumulates in tissues and fat, leaving little in plasma. A very high VD, like 500 liters, means the drug is heavily sequestered in tissues, with only a tiny amount remaining in the plasma. To summarize, volume of distribution is a theoretical volume indicating how a drug distributes in the body. It's affected by lipid solubility, protein binding, tissue affinity, and physiological factors. It's vital for calculating loading dose and understanding half-life. Drugs with a large VD distribute widely and may have a prolonged duration of action. In essence, VD tells us how deeply a drug travels within the body after administration. It bridges pharmacokinetics and clinical pharmacology, guiding dosing, predicting accumulation, and explaining toxicity patterns.